So a couple people sent me or suggested some questions that we discussed, and I've embedded those in the lecture, so that should be a nice way to talk about a couple extra examples today. Our lecture, after I looked it over this morning, it looks like it'll be a little shorter, so maybe we won't go over time this time, hopefully. But if anyone does have any other questions, feel free to text them on the lecture text channel or unmute yourself and speak up anytime, including right now. Alright, so we will talk about today's quiz questions as we go through the lecture, and then I will also give you individualized feedback on your answers within your Google Docs. Just to remind you, when I look at your quiz answers, I will be looking at the history of the document to make sure that what you've written for your answers was written before 1 p.m. So please make sure that you get started on those early enough that you can get them turned in and completed, so the history of your document reflects that. If you have to finish anything up now within the next 5 minutes or so, that's fine. I won't take off points for that, but generally you want to make sure that you're not making changes to your document after 1 p.m. until it's been graded. Alright, so last time we were talking about resonance. We showed all the different ways for you to look for electron movement. There were those 5 patterns we talked about. Maybe we should just review those real quick. So I don't know them in any particular order, but one of them is a situation where you have an allylic carbon cation. So any time you have a positive charge not directly on the double bond, right? This would be a vinylic carbocation. That's really unstable, and we don't really ever much see that. If you have an allylic, though, that consists of a p orbital overlapping with the p orbitals of the double bond, and the electrons can shift over there, and so that's one pattern, the allylic carbocation. Another one is an allylic lone pair. So whenever I have a lone pair, again, not a vinylic lone pair, it would be right on that carbon involved in the double bond, but allylic means one carbon away from the double bond. That can shift in here and push these electrons over here. Okay, so the biggest mistake students make here is just using one arrow. If I have my allylic lone pair and I only move that in, that's all. It might not look that bad to you, but there's a hydrogen here or something else bonded. There's got to be 4 bonds, so moving the allylic lone pair in creates a 5 bonded atom, which is not possible if it's a second energy level atom. So you have to also move the other electrons out at the same time. So that's pattern 2. A third pattern involves a situation where you have 2 atoms sharing electrons. As long as they're sharing both a sigma and 1 or more pi bonds, if there's an electronegativity difference between them, like between carbon and oxygen, that's the most common one you'll see, then the electrons can shift up because they're more attracted to the more electronegative atom. Another one exists when you have that one is skipping my mind at the moment. There is yes, this one is also not very common because positive charges aren't really that stable, but if you have a positive charge on an atom and that's adjacent to something with a lone pair, as long as that positive charge is a situation where it can accept more electrons, those electrons can swing in there and make a pi bond. So it's really the opposite of this situation. If I move these electrons up to create a lone pair, when they move away from this atom, assuming it was neutral to begin with, it'll become positive. and so the electrons can always move back down. So 3 and 4 are kind of the opposites of one another. One situation where 4 will not work is where you maybe have a nitrogen that's positive, and that's adjacent to a lone pair. Right. This nitrogen already has 8 valence electrons. It cannot accept more. It's a second energy level atom, so I cannot push those in and make a 5th bond to it. And then the 5th one, which is different from the rest and which makes it easier to remember, is a situation where you have the 6-membered ring is the most common, but a ring with alternating double, single, double, single, double all the way around. That pattern would involve all of the pi electrons in the ring shifting one position over to just create basically the same looking structure, but the electrons would move one position over. So they would be now here, here, and here. And you might say, well, what's the point? Basically, it looks like the same structure. I just rotated it a little bit. Well, the point is not that the structure is different, but the point is for you to recognize that since those electrons can shift, that neither of these actually exist. What exists is the resonance hybrid, which is what we're going to talk a little bit about today in the beginning. So picking off where we left off, if those electrons are in resonance, they're not localized in any one spot between any 2 carbons. They're also not here and then later over here. They're instantaneously in a molecular orbital that extends over all of those atoms. So the dotted line serves 2 purposes. It allows us to get a sense for which atoms this molecular orbital extends over, that the electrons exist in. And it helps us understand that the nature of the bonds here, right? So if I have a single bond between 2 atoms, like this one here, right? There's no double bond, just a single bond there. That has a certain strength and a certain distance. My double bonds, where I might have the pi bond and the sigma bond together, are shorter, they're stronger. But since resonance means that neither of those actually exists, what exists is the electrons existing all over all 6 atoms, each one of these bonds, or connections between any 2 carbons in the ring, the strength of that bond is somewhere in between the strength of a single bond and the strength of a double bond. And it's somewhere in between the length of a single bond and the length of a double bond. So not only do the electrons exist in a molecular orbital spread out over multiple atoms in resonance, it also affects the bonds themselves. The characteristics of the bonds are somewhere in between the single bond and the double bond, or they're the average of what we see in the individual contributors. The hybrid is the average of the individual contributors. So anytime we can see that in one contributor a position has a single bond, maybe in another contributor has a double bond, well, the reality of that situation is it's more like a bond and a half, or it's a bond plus a partial bond, and it has the characteristics in between the typical strength and length of a single bond and a double bond. So in order to do this, we're focusing on these 5 patterns. So how do we know when electrons are in resonance? Well, we look for the 5 patterns. But there's a little bit more to it than that, because there are some situations where you may be able to recognize one of these 5 patterns as possible, but it's not really possible. And so we have to understand the reasons for some of these exceptions so we can identify them and not think that there's resonance when there isn't, or more commonly vice versa. Right, so the most common ways that we find resonance are these 5 patterns, but sometimes the 5 patterns don't actually lead to resonance, and we want to look out for those situations. So the bottom line for resonance, as we were saying over here, is for resonance to occur, I can look for these patterns, right? I can look for this lone pair to move in here and move these electrons out. That's the allylic lone pair pattern. But in order for it to actually work and be possible, it does rely on p orbitals. So I have to have p orbitals here to create this pi bond, as they overlap side by side and interfere constructively and destructively. The 2 pi electrons will be in the constructively created bonding molecular orbital. In order for this lone pair to engage in resonance with the other pi electrons, there has to be a p orbital for it as well. So any pair of electrons that I would imagine moving with these curved arrows has to be in a p orbital overlapping side by side with the other p orbitals in order for it to actually engage in resonance in the real world. So to be delocalized over multiple atoms in a molecular orbital, there has to be the ability to create that molecular orbital by overlapping unhybridized p orbitals side by side, both above and below the plane of where the nuclei exist. So that means those electrons must be on an sp or sp2 hybridized carbon, because those are the only types of carbons that actually have unhybridized p orbital, right? Obviously sp3, there's no empty or existing even p orbitals because they're all mixed in with the s to make the sp3 orbitals. So any sp3 atom cannot involve any of the electrons around it in resonance, because those electrons would have to be in a p orbital, and there are no p orbitals on an sp3 hybridized atom. So let's look at some examples to illustrate that idea. So typically, if we want to know whether an atom's sp2, sp, or sp3, we look at the steric number, right? So for example, this carbon here, that carbon's steric number, it has, the steric number is the sum of the sigma bonds plus the lone pair, so it has 1, 2, 3 sigma bonds. It doesn't have any lone pairs, so its steric number is 3, and if the steric number is 3, it's going to be sp2. So that is what we would expect, because we expect the pi electrons to require a p orbital, and so we can't hybridize all our p orbitals into making sp3 if we need one of them to still exist here for the carbon and oxygen to overlap side by side and create the pi bond. So an atom has to be it has to be sp or sp2 in order to engage in resonance. It can't be sp3. So let's take a look at the nitrogen. How do we analyze the hybridization of this nitrogen? Well, we would use the steric number. So for the nitrogen, the steric number should be 4, because it has 1, 2, 3 sigma bonds and 1 lone pair. So that's 4. Normally, if the steric number is 4, that should be sp3 hybridized. So if we're to draw the structure and looking at the orbitals that are involved, the carbon here would be sp2. It would have an sp2 orbital to overlap with the nitrogen. It would have an sp2 orbital to overlap with the carbon or the oxygen. And it would have an sp2 orbital overlap with this other carbon group represented with the letter R, whatever, it could be some generic carbon group. And it has an unhybridized p orbital because it's sp2, and that overlaps side by side with the p orbital of the oxygen above and below the plane of the molecule. So let's take a look at the nitrogen. What we said is, based on the steric number, we would predict the nitrogen would be sp3. Typically 3 bonds in a lone pair creates an sp3 hybridized atom. So if it were sp3, it would use one of those sp3 orbitals to overlap with the carbon. It would use one to overlap with one of the 2 R groups attached to it. It would use another to overlap with the other R group. And it would use a third sp3 orbital to hold its lone pair. So that looks pretty good. That's what we would normally predict. But in that situation, the lone pair of the nitrogen cannot be involved in resonance. So even though we see there's an allylic lone pair, it's allylic to this CO double bond, and we think of it being able to move in, if the lone pair existed in an sp3 orbital, it would not be able to engage in resonance. So what's the other option there? I'll just focus in on that. Well, actually, let me just... just focus in on that part of the molecule and redraw it here. So this carbon is forming the sigma bond with the nitrogen. So the nitrogen could be sp3, but let's imagine, what if it hybridized sp2 instead? Then it would have to use its sp2 orbitals to overlap with these R groups to make the sigma bonds, and then it would have an unhybridized p orbital to hold its lone pair. And since the carbon has a p orbital and the oxygen has a p orbital, as we discussed, overlapping to make the pi bond, then the lone pair could overlap side by side and make resonance. So sometimes you really have to think about, is this lone pair going to exist in a p orbital, or is it going to exist in an sp3? If it exists in a p orbital, I can have side by side overlap and allow for resonance. If it exists in an sp3, I don't have that option. So what's the more stable situation? Well, normally, if I just have the nitrogen's lone pair, and let's just say it wasn't bonded, it wasn't allylic, so instead of being one atom away from a double bond, let's just say maybe there's a hydrogen here. If there's a hydrogen and maybe a couple other sigma bonds with these other R groups still, then it would be better to put the lone pair in an sp3. Because an sp3 versus a p orbital, the sp3 is more compact. It has some s character mixed into it, which makes the shape of the orbital more spherical and holds the lone pair a little bit closer to the nitrogen, stabilizing the lone pair. So that's why a lone pair typically exists in a hybridized orbital, sp, sp2, or sp3, because they're more compact than an unhybridized p orbital, which is more elongated shape. So that's why normally we would expect this to be sp3 because of its steric number of 4, because the lone pair is more stable in a more compact orbital and lower in energy than it would be in a more elongated orbital. So here's the exception. If the elongated orbital can be directly next to another atom with the same type of orbital overlapping side by side, that is when it's more stable to be in a p orbital. So despite the elongated shape of this orbital holding the electrons farther out from the nucleus, because now a new molecular orbital is going to be created due to the overlap of all three, that actually more than enough stabilizes this lone pair by allowing it to exist over in a molecular orbital, attracting to more nuclei. And so even though the orbital is more elongated, because that orbital disappears when the molecular orbital is created over all three atoms, the electron is going to be more stable in a molecular orbital than just in an atomic sp3 orbital. Okay, so this is important. It's an exception where even though we normally calculate the steric number to determine the hybridization, in this case, it's not correct. It's not an sp3 hybridized atom. The nitrogen does not end up sp3. It ends up sp2. It uses the 3 sp2 orbitals it creates to overlap with the R groups and the other carbon to make the sigma bonds, which leaves the lone pair in a p orbital specifically so that the lone pair can be stabilized by the side-by-side overlap with the neighboring p orbitals. So that only works when it's conjugated, which means the p orbitals are all on adjacent atoms overlapping side by side. So to allow for the lone pair to be engaged in resonance, sometimes an atom that would normally be sp3 actually ends up being sp2. That way the lone pair can be in the same type of orbital that exists on the neighboring atoms overlapping side by side on the top and side by side on the bottom to make that extended molecular orbital that really stabilizes the electrons. That's what gives resonance. It's stabilizing force. So we calculated the steric number. We said the nitrogen has a steric number of 4. That would normally make it sp3, but in this case, if it were in an sp3 orbital, it would not be able to engage in resonance because it wouldn't have the side-by-side overlap. The sp3 orbital is kind of angled off to the side, and it's not pointed straight up and down where it can get close enough to really overlap. So we wouldn't really have much overlap there. It would be very minimal. So it really needs to be at a p orbital to get close enough for the side-by-side overlap to occur for the resonance to stabilize it. So that's why we have a nitrogen. If a nitrogen is directly connected to a double bond, its lone pair will exist in a p orbital and the nitrogen will be sp2 hybridized. So that's what we're saying here. And then we answered this question. Why would it normally be better to sp3 versus sp2? Well, and we mentioned that over here. If the nitrogen is not allylic, then the sp3 orbital is more compact than the p orbital, so it's better to put the nitrogen in the more compact orbital normally. The only reason they would go into a p orbital is if there are neighboring p orbitals that it can overlap side by side with and be stabilized by. And we see the picture of that here. Right, so here are my p orbitals, the red and blue here are both part of the same orbital. There's overlapping and constructive interference on both the top and the bottom. And so the side-by-side overlap there is what allows the lone pair to be stabilized through resonance, and that is why the p orbital even exists versus the normal situation where you'd have the lone pair in an sp3 hybridized orbital. Delocalization or resonance always requires p orbitals overlapping side by side. And so that's a key thing. We got to analyze the hybridization of the atom if we expect to be able to see the orbitals that are there and to confirm that the p orbitals exist so they can actually overlap and create resonance. So there's an instance where you might not have predicted the resonance if you didn't understand that the lone pair exists in a p orbital instead of the normal sp3 that you would normally expect there. So you got to look out for that. So let's look at the resonance hybrid. So now that we've established the lone pair exists in a p orbital, overlapping with the p orbitals of the carbon and oxygen, now we can be confident that our allylic lone pair pattern that we talked about last time, which creates an alternative resonance contributor, is a reasonable way to show two different contributors that would contribute to the real structure. But again, we said the individual contributors that show the electrons localized in one spot or in another do not exist. What exists instead is the resonance hybrid. So again, to draw the hybrid, we just redraw everything that's not delocalized, everything that's exactly the same in both structures is not involved in resonance. So obviously the sigma bonds are not part of the resonance. Resonance only involves electrons and pi bonds. So I can draw all the sigma bonds. I can draw any lone pair that's not involved in resonance. So if I look at the oxygen, there's two lone pairs here, three over here. So two of those three are not delocalized. Two of them aren't moving anywhere. So two of them are going to be there all the time. The third pair of electrons could be here on the oxygen, or it could be in here. And the lone pair on the nitrogen could be on the nitrogen or in here. So since those ones are involved in moving, or they are delocalized, we don't show them, we represent them with the dotted line indicating which atoms their molecular orbital extends over due to the p orbital side-by-side overlapping. And that dotted line accounts for both the pairs of electrons that are involved in resonance. So a lot of times students draw the resonance hybrid and they stop there. You also have to show any charges that are present. So what charge is on this oxygen? Well, since the hybrid, or true structure that actually exists, is the average of the individual contributors, well then the quantity of charge that exists on that average, or on that oxygen, should be the average of the charge that we're seeing on the oxygen in the individual contributors. So this has zero charge, and this has a negative charge. So is it fair to say that it should be exactly halfway between 0 and -1, or -1/2? The degree to which the average charge is impacted by one contributor or another has to do with how stable the contributors are. Right, so I also have to look at how stable these contributors are. This is pretty stable. There's no formal charge anywhere. So I've got complete noble gas configurations or octets everywhere, no formal charge. This is a stable structure. So this is my major contributor. This one over here has these two unnecessary formal charges. It still has complete noble gas configuration, so it's not prohibitively unstable or insignificantly, or I should say it's not unstable to the point where it doesn't contribute at all, or that its contribution is insignificant. It's still a significant contributor, but the charges make it less stable, so it's a minor contributor, which means that the quantity of charge on the oxygen shouldn't be exactly halfway between those values. If this is the major contributor, it's going to contribute more to what the average looks like. So instead of saying that I can say that it's exactly -1/2, it's probably more reasonable just to put a partial negative there to indicate I only have a small amount of charge, because for the most part this atom's neutral, but there is some degree of contribution mixed in where it does take on a slight bit of negative. And then the same type of argument for the nitrogen. The quantity of charge carried by this nitrogen is between 0 and +1, but probably closer to 0 than to +1, because this is a major, more stable contributor. And so I just put a little bit of a partial positive to indicate that nitrogen carries some positive charge due to the existence of this minor but significant contributor. Questions about that? All right, so here's another example. So here's an example where the lone pair here exists on an atom. It's an allylic lone pair to this double bond. So that matches one of the patterns we talked about. So if you only memorize and practice the patterns, but don't look at the orbitals that the electrons exist in, you may get some of these wrong due to the fact that some of the patterns don't work. In order for the patterns to work, the atoms involved, so these two carbons that have a double bond, and the nitrogen, the electrons that would be moving, right? So I can see this allylic lone pair, I can say, well, this should be able to move in here and push these pi electrons onto that carbon. In order for that to be possible, though, the lone pair has to exist in a p orbital that can overlap side by side with the p orbitals on the neighboring atoms. So you say, well, that looks reasonable. What's the problem? Well, the problem is this lone pair is not in a p orbital. I can draw it in a p orbital, but that's not where it is. So how do I know what orbital the lone pair is in? Well, the key here is that there's another double bond on the other side. Right, so if we look at this nitrogen and what the situation that it has, this nitrogen has a pi bond already shown with another carbon. That means that its p orbital is already occupied with the electrons involved in this pi bond. The lone pair cannot also be in the same orbital because it's already occupied with a pair of electrons. And so if I have a lone pair that's allylic to a double bond, I can draw this, but it's not possible because that lone pair is also vinylic, which means it's also on an atom that's already engaged in a double bond. And so it can't be in a p orbital if the p orbitals are already occupied with electrons due to being part of a double bond or a pi bond. So what is the situation with the lone pair in this nitrogen? Well, it's hard to draw, so there's a nice picture over here from the textbook. Right, so this is what we see with this nitrogen. Right, so we said if we draw the pi electrons in where they were in that structure, we said this nitrogen already is part of a pi bond. It's already engaged in double bonding. So its p orbital here is already overlapping with the neighboring carbon's p orbital. The lone pair cannot also be in that orbital. And so if we look at the hybridization of that nitrogen, it's got 1, 2 sigma bonds for its steric number, 2 sigma bonds and 1 lone pair. And so we would expect it to be sp2. And it is. It has 1 unhybridized p orbital to form the pi bond, but then that means that the lone pair must be in one of the 3 sp2 orbitals around it, which means it's perpendicular to the plane of the pi electrons. Right? So again, electrons cannot be involved in resonance or delocalization unless they're in a p orbital, and if they're in a hybridized sp, sp2, or sp3 orbital, they're perpendicular to a plane of any existing p orbital, and so there's no overlap that can occur there. And so this lone pair is not delocalized. It's localized on one atom. It's not part of the resonance. So there is resonance here, but it's not this. It's not the allylic lone pair. So I do have an allylic lone pair, but that lone pair is not in a p orbital, so it can't actually do the allylic lone pair pattern. It's stuck on the nitrogen. So the only pattern I have here is the alternating double and single bonds around this ring. So those electrons are all in resonance, and they can move around, but it does not involve the lone pair. The lone pair is not involved in any kind of resonance in that situation. Because the lone pair is positioned in an orbital that cannot overlap side by side with those p orbitals, it cannot be involved in resonance with them. Any questions about that? All right, so here's an example suggested by a student to look at today. This is a great example because it dovetails along with exactly what we just said. And the question here is to look at the lone pairs and try to identify which ones can be delocalized in resonance versus which ones are stuck on the atom that they're starting on because they're not in a p orbital and they can't get involved in resonance unless they're in a p orbital. So let's take a look at A. The nitrogen has a lone pair, and so does this one. Which nitrogen, if any, can be engaged in resonance? Well, if I look closely at this lone pair, I see that it is allylic to this pi bond. So according to the patterns we talked about on Tuesday, I could imagine moving these in and moving these out to the carbon. If I did that, my structure would look like this. This pair of electrons would move out to the carbon, so it would be here. Nothing else is changing anywhere. That would create some formal charges, but it wouldn't be super unstable because at least all the atoms have octets or noble gas configurations. So as far as the allylic lone pair pattern goes, that's reasonable, but to verify that it's possible, I have to at least be able to imagine that this lone pair could be in a p orbital. So what is the steric number and hybridization of this nitrogen? The nitrogen has a steric number of 4. It's got 3 sigma bonds and 1 lone pair, which normally means it should be sp3. So if I made it sp3, the lone pair would have to be in an sp3 orbital. It wouldn't be able to be stabilized by resonance. So that's probably not the most stable arrangement for it. If the resonance is possible, it's usually stabilizing it, and we want to try to get the molecule into a situation where it can do that. So instead, I would imagine that lone pair in a p orbital. I would imagine and recognize that the nitrogen should be sp2 hybridized. It should have sp2 orbitals to make its sigma bonds to the ring. And the lone pair is going to exist in a p orbital, so that can overlap with p orbitals all the way around the ring. So that lone pair should be possible to delocalize because it can form a it can exist in a p orbital that would overlap with the other p orbitals all the way around both the top and the bottom of the ring. And so this resonance is significant and possible, and it does stabilize this lone pair of electrons. What about the lone pair over here? This lone, yes, go ahead.
I have a quick question. So with it having a steric number of 4, so it would be sp3. If it was localized localized, would it stay at sp3? And if it was able to be delocalized, would it be sp2 then?
Yes. So,
Okay.
so it's not like, so that's a great point. An atom's hybridization, so in this case the nitrogen, whether it's sp2 or sp3, it's not something that's locked in. It's not something that, okay, it's not like this is how it exists. It has options. It can hybridize however it needs to hybridize to be as stable as possible. So typically, and that for a nitrogen like this one, if it has 3 bonds, 2 of them are to hydrogens and 1 is to a carbon, 3 bonds in a lone pair, normally it's more stable to make it sp3 because having more sp3 orbital hold the lone pair is usually more stable than having the more elongated p orbital hold the lone pair. The exception to that is when the p orbital is conjugated or can overlap side by side with other p orbitals, because then that allows for resonance and delocalization. And since that's stabilizing, that more than it stabilizes the electrons so much that they're more stable in the more elongated orbital that's overlapping than they are in the more compact orbital that's not overlapping. So the key here is this nitrogen takes on the expected sp3 hybridization because the neighboring atom is also sp3 and doesn't have any p orbitals to overlap with this nitrogen. So the nitrogen in effect chooses to put the lone pair in an sp3 because it's more compact and stable than it would be in a p orbital if there's no p orbital on the neighboring atom to overlap and help to delocalize and stabilize the electrons. So bottom line is, for nitrogen, if the lone pair, or if the nitrogen's lone pair is adjacent to an atom that also has a p orbital, it will be sp2 and the lone pair will exist in a p orbital to overlap side by side because that stabilizes the lone pair more. If not, and the neighboring atom's just sp3, then the lone pair will exist in an sp3 orbital and the nitrogen will be sp3 hybridized because that compact shape of the sp3 stabilizes the lone pair more than if it were in a p orbital. Let's take a look at this one, B here real quick. So B is a similar situation to the one we talked about on the lecture slide. The oxygen has 2 lone pairs, the nitrogen has 1, this oxygen has 2. So we have a lot of analyzing to do to decide which of these lone pairs can be delocalized and which can't. So we can look at this top oxygen first. On the top oxygen, there is already a p orbital or a pi bond. So the electrons in that p orbital already exist in the pi bond. So the lone pairs can't also exist there. So that's a situation where that oxygen is going to be sp2 because its steric number is 3. It's going to have sp2 orbitals to hold the 2 lone pairs. Oops. sp2. It's going to have an sp2 orbital to overlap with the carbon to form the sigma bond. And then it's going to have a p orbital to create its pi bond. So the side-by-side overlap of the p orbitals between the carbon and the oxygen is why those atoms are sp2. That allows one pair of electrons to exist in that area of overlap to create the pi bond. So both of these lone pairs are localized. They cannot be engaged in resonance unless they're in a p orbital, and they can't be in a p orbital because it's already occupied by the pi electrons. So what about the other oxygen? Well, this carbon has a sigma bond with the oxygen. It also has a sigma bond with the nitrogen. So this oxygen has 2 lone pairs and obviously has another sigma bond, and so does the nitrogen. The nitrogen has 1 lone pair. So as we were just saying, if the atom is adjacent to an atom with a p orbital, it would be more stable to put the atom's electrons in a p orbital to overlap side by side. And so that's the situation we have here. Because this oxygen and this nitrogen are directly connected to the carbon, and the carbon has a p orbital, it'd be more stable for this nitrogen to sp2 hybridize and put its lone pair as well in a p orbital that can overlap side by side with the carbon's p orbital. That allows that lone pair to be involved in resonance. Same thing with the oxygen. I can't do that for both lone pairs, so when the oxygen hybridizes sp2 and puts one of its lone pairs in an sp2 orbital, the other lone pair will exist in a p orbital that can overlap side by side with the carbon. And so all of that side by side overlap creates this big molecular orbital that extends over multiple atoms and allows the delocalization of one of the electron pairs on the oxygen and the electron pair on the nitrogen. Both of those are allylic to the double bond. Both of those can exist in p orbitals to overlap side by side with the p orbitals of the CO double bond, and that's what allows them to be delocalized, whereas this lone pair and these up here are localized because they would have to exist in sp2 orbitals rather than p orbitals. So you start to see a pattern. If the lone pair is allylic, as long as that atom doesn't already have its p orbital occupied, then the lone pair can be in a p orbital and overlap side by side. So let me just point that out real quick. As we said before, let's say this is my nitrogen here. Right, this is an allylic lone pair right here. It's allylic. It can be in a p orbital unless the atom already has its p orbital electrons occupied. So if this lone pair is on the nitrogen and it's allylic, normally it could be in a p orbital and overlap side by side and create resonance, but in this case, since the p orbital is already occupied with pi electrons, that can't happen. So there's a significant difference between this and this. The nitrogen here doesn't really need to have a p orbital, so it can make one to hold the lone pair, and then that can overlap with the p orbital on the carbon and the oxygen and do resonance. Here, the lone pair can't be in that p orbital because the pi electrons are already occupying it. So that's a key thing that you want to look for there. So that's a situation here. This nitrogen already has electrons in its p orbital, so the lone pair has to be in an sp2, and it can't be involved in resonance. Here, that's not the case. Here I can put the lone pair in a p orbital, and it can overlap with the p orbital on this carbon-carbon bond, which will overlap with the p orbital on this carbon-oxygen bond. All of that overlap helps to stabilize the lone pair and the pi electrons there, and so that means that this nitrogen here would be sp2 and its electrons are going to be in a p orbital engaged in resonance to be stabilized. So, I mean, there's more there we could talk about, but I think that does a pretty decent job of covering. Any questions about that? Alright, so that leads us to the first quiz question for the day, drawing the resonance hybrid. We have to look at the pattern. So last time we talked about all the resonance contributors. So you can go back and look at the video from Tuesday's lecture if you want to recall what the individual contributors were. But we said one of those involves electrons moving in here. So for the hybrid, the electrons could be drawn on the oxygen in one contributor or in the space here in another contributor. So where are they really? Well, they're in both those locations at the same time, which means that we should show that with a dotted line. The lone pair in the sulfur is not involved in resonance, so it's just stuck there. So in that area of the molecule, we had two contributors. We had one where the sulfur was positive and one where the sulfur was neutral, right? The other contributor had a double bond there. So which of those contributors is the major and which is the minor? That's hard to say. I wouldn't expect you to necessarily recognize that. This one has the advantage of at least having a noble gas configuration or octet for the sulfur. This one doesn't have that, but this one has the advantage of not having any unstable formal charge. So they're probably similar in stability. The true structure in reality is slightly more like this one due to the noble gas configuration. So even though this contributor has full charges, because this has no charges and it is significant and factors in, the average amount of charge on the sulfur is going to be between 0 and 1. So it's going to be a partial positive. The average charge on the oxygen is between 0 and -1, right? We're averaging the two contributors together to find out what the real structure looks like. And so the average between 0 and -1 is a partial negative. So that's how we would represent that part of the molecule in our hybrid. So then we would continue drawing. Oops. We can, if you want, we can just draw out the all the sigma bonds, because those are not moving. The boron is sp3, so it's not involved in any resonance, so you shouldn't have any dotted lines extending over to the boron. Right, so there are all our sigma bonds. So let's take a look at this area of the molecule. We said last time that this pair of electrons could shift down here, and this pair could shift in there. So if this pair shifts down, negatively charged particles attracted to a positive atom. It's an allylic carbocation. If those shift down, they could be in either location, and so my dotted line would reflect that. This lone pair can shift in here, and so I need a dotted line there as well. When the lone pair shifts in, there's still two lone pairs on the oxygen. So there's two lone pairs on the oxygen that are not delocalized or that are not in resonance. But there's still some charges around here that need to be dealt with. So the positive charge here in one of my contributors is going to go away when I move these electrons down. So the hybrid or average means I only have a slight partial positive there. Only one contributor has a positive, the others have a neutral charge for this carbon. So the average between neutral and positive is a slight partial positive. When these electrons move down, temporarily it'll create a little positive there. So this carbon is going to have a little bit of positive in my hybrid. Once the oxygen swings its lone pair in, that will neutralize that. So it's not a full positive, it's only a partial positive because the positive is only there due to one of my contributors being positive and the others are neutral. So the average is going to be only a little bit of positive. And the oxygen, this contributor is negative. Once the electrons swing in to make a double bond, it'll become neutral. So the average between neutral and negative is going to introduce a slight amount of negative on that atom. So dotted line everywhere where the electrons are moving, partial charges due to the fact that each of these atoms, on average, has some quantity of charge between 0 and +1 or between 0 and -1. I still want to represent my full negative on the boron because that's its formal charge and it's not changing at any point. There's no way to shift electrons around there in resonance when all it has is sigma bonds around it. So then the last part that actually does involve resonance, I've got this contributor. The other contributor would be created when this pair of electrons moves to the oxygen. So that pi pair of electrons can be involved in resonance. There's one lone pair that's not moving, so that'll still be there. And this oxygen's lone pair could shift electrons in, so I need a dotted line here as well. So what quantity of charge then should be shown? Well, the oxygen, if this pair of electrons moves out and becomes a lone pair, two lone pairs and two bonds would give it 0 charge. So in reality, there's one contributor with 0 charge, one contributor with a +1, so the average amount of charge there is going to be a little bit of a partial positive. In this contributor, the nitrogen has a -2. If the electrons swing in, and it looks like this, it has a -1. So where one contributor has a -2 charge and the other has a -1 charge, this is more stable because it's less charge overall. So that would be my major contributor. But the average is still going to be between -1 and -2. So here I could say some quantity of negative that's probably The amount of negative here is greater than -1, but less than -2. And that's hard to really explain, or to communicate in writing, but you could also put a -1 point something. We don't know exactly how much, but -1 point something would also be an acceptable way to represent the quantity of charge there. And then the only thing still missing is there are two lone pairs that are not involved in moving, so I need to show those two localized lone pairs since they're not involved in any resonance. If you just put a partial negative on the nitrogen, I probably wouldn't take off points, but technically that implies that the charge is between 0 and -1, where in reality it's between -1 and -2, because those are what the contributors, those are the quantities of charge the contributors are carrying, and the real structure is going to be the average of that. Questions about that one? Alright, so that's it for Chapter 2. Chapter 3 should be pretty easy for you if you did well in Gen Chem 2. Most of this stuff is much more basic than what we talked about in terms of acids and bases in general chemistry 2 especially. But we want to review some of this stuff because it turns out acid-base reactions are some of the most common types of reactions that occur with organic compounds. So we want to be real familiar with these. So if you recall from general chemistry, the Brønsted-Lowry definition is that an acid donates a proton, and a proton is simply an H+. Right? So my acid molecule is going to be one that has a hydrogen that's kind of loosely held, and the other atom can pull the electrons away strongly enough that that hydrogen's nucleus, which is just the H+, which is just simply a proton, because normally there's no neutrons in there, and if the electrons get pulled away, there wouldn't be any electrons associated with it either. The hydrogen's nucleus, or proton, can be lost. It's not going to be lost usually and go off on its own, because as a simple proton, it doesn't have any electrons, it doesn't have a noble gas configuration, it's really very unstable. So typically an acid won't be able to do its thing and donate a proton unless there's a base around that can use a pair of electrons to start sharing with that proton. So that's an acid-base reaction. The acid gives away the H+, the base brings its lone pair in and accepts the H+ from the acid. So it's a transfer of an H+. That's why these reactions are often called a proton transfer. That terminology is going to be used a lot in this textbook. So proton transfer is simply an acid-base reaction by the Brønsted-Lowry definition, which is by far the most common definition. So once the proton's transferred, you want to draw the products that result from that. The oxygen picks up the proton, it now has a new bond to that proton, which happens to create a formal positive for it. The chlorine keeps the electrons behind, so it now has an extra lone pair. It's not sharing them with the hydrogen anymore. So now that all those electrons are owned by itself, it creates an extra negative charge. Every acid-base reaction is reversible. So we could also imagine the chlorine then acting as a base to pick the proton back up, and these electrons here could stay on the oxygen and reform as a lone pair. So in the reverse reaction, this would be the base, because it would use the lone pair to pick the hydrogen up. This would be the acid. And if you recall, we use the term conjugate to describe those. This is a conjugate base of HCl because it's formed when HCl donates a proton, and now it has at least the potential to pick the proton back up, which makes it a base. And then this would be the conjugate acid of water. Conjugate acid of water, because when water picks up a proton and becomes more acidic, it's now the same structure, but it just has one extra proton that it could then donate and go back to its original form. That's what makes it an acid. So there are lots of acid bases and a lot of reactions that involve them that we're going to see throughout the semester. Here's an example here. We've got this carbon structure with a negative charge on my oxygen. So we know a negative charge usually makes a pretty good base, because a negative charge has the ability to attract an H+ or a proton, and a base's role in a reaction is to pick up or accept a proton. So if we pick up a proton from here, that arrow, remember the curved arrows we talked about in resonance, we're going to apply them now to chemical reactions, not just resonance. So the rules for the curved arrow are the arrow starts on a pair of electrons. It ends where the electrons are going to go. Right? So there are a couple ways you could interpret this. One is you could say, well, this arrow is suggesting these electrons are going over here to the hydrogen. So maybe that produces a hydrogen with the electrons, and then the oxygen doesn't have them anymore. Is that reasonable? No, that's not reasonable. So you have to use some chemical expertise to recognize that if this arrow were indicating that the lone pair is just leaving the oxygen and going to the hydrogen, that would create a negative, and that would create a positive, and the oxygen wouldn't have enough electrons to make its octet or noble gas configuration. That would be really unstable. So that's not what we're talking about with this arrow. When we're talking about using curved arrows in a reaction, if the arrow starts on a lone pair and ends on an atom, we're just talking about forming a bond between those two. So the lone pair isn't actually leaving the oxygen, but it is being used to start sharing with the hydrogen, and that's what that arrow is communicating. If that were the only thing happening, though, the hydrogen would still be bonded to the oxygen that it's originally bonded to. So in any proton transfer or acid-base reaction, if you're using arrows, you always need two arrows. One arrow to show the bond forming, and one arrow to show the other bond breaking. There's always one bond forming and one bond breaking in a proton transfer step. So when this bond forms, this bond has to break to avoid 4 electrons around the hydrogen, which would be really unstable. So when this bond breaks, it creates the extra lone pair on that oxygen. So that's what this arrow is communicating. It's showing this pair of electrons is no longer going to be shared. Now it's going to be just on the oxygen, and that's where we see it. Right, so this is my base. Water in this case is acting as an acid because it's donating a proton over to the base. And then these are my conjugates. The base forms a conjugate acid because now it could potentially lose that proton. Right, if I did the reverse reaction, this would be the acid because it would donate the proton over to the oxygen, and these electrons would stay behind here. And then this is my conjugate base, because if we were to do the reverse reaction, this one would be the one picking up or accepting the proton, which is what makes it a base. So when you're identifying the products as acids or bases, look at them from the point of view of what would they have to do in order to go back to the left-hand side of the arrow. Alright, so let's draw some products here. So here, if I tell you which one is the acid and which is the base, all you have to do is know what the definitions are and follow them. Right, so if I know it's a base, I know it's going to be using its lone pair to pick up a proton. If I know it's an acid, it's going to be giving the proton away. Do not start your arrow on the proton. That's not right. We're all communicating in the same way here. The convention is we only use the arrows to show electron movement, not atoms movement. You should never, ever, ever start an arrow on a hydrogen. There's no electrons there. So that's a bad arrow. What's happening is the electrons are picking up the hydrogen, and these electrons are staying behind. So when this nitrogen picks a hydrogen up, now it has 2 hydrogens instead of 1, and it takes on a positive charge. The oxygen pulls these electrons behind, and so it has a negative charge. So this is then the conjugate acid, because now it could donate the proton back over the oxygen and go back. So if it has the potential to donate a proton, it's an acid. This one is a conjugate base, because it could pick that proton up. And if I were to show the arrows to indicate that electron movement for the reverse reaction, the arrows would start on the electrons, go to the hydrogen it's going to form a bond with, and this arrow would start on these electrons and show which atom those electrons end up on as a lone pair. I could imagine those two same molecules, though, reacting differently, where now instead of the nitrogen's lone pair being the base, this one has a proton. It could donate. It could be thought of as an acid, This one has a lone pair it could use to pick up a proton. It could be thought of as a base. So an alternative electron movement you might consider here, it could look like this. If this is the base, its lone pair would pick up this proton on the neighboring molecule. If this is the acid, its electrons would be pulled back, and that would create these two conjugates. This would be my conjugate base. This would be my conjugate acid. Because if I were to consider the reverse reaction, this one would have to pick this proton up in order to go back, so it would be a base, and this one would have to lose a proton to go back, so it would be an acid. So we think of water as being neutral. That does not mean that it's neither an acid nor a base. Water being neutral specifically means that it's equally likely. Oops. What neutral means for water is that it's equally likely to be an acid or a base. And so for water it means the substance I put in with the water is what determines what the water does. Because the water doesn't care. It can be an acid, it could be a base. If I put the water in with an acid, the water acts as a base. If I do the opposite happens. So in this particular case, I have to look at the other compound. This compound here, is this more likely to be an acid or a base? How do I know? Well, the standard is it's an experiment I have to do. So if I want to know if this molecule is more of an acid or more of a base, I can, on paper, draw it either way. I run the experiment. I take this compound, I put it in water, because water is my standard. It can go either way with equal probability. So I put that in water and I look at the products. Do I get more of this in water, or do I get more of this? And if you do that experiment, you'll find you get a lot more of these products and almost none of these products. So even though I could imagine the reaction happening in either way, these are the products that I get experimentally, which means water in this circumstance acts more as an acid because the nitrogen's lone pair is more basic. Or in other words, the nitrogen is more stable with a positive charge overall than with a negative when it's dissolved in water. Alright, so we talked about the curved arrows. Curved arrows are going to be a huge part of this class, which is why we have the mechanism app. So hopefully that will help you visually to imagine what these things look like when their electrons move from one place to another. But you definitely want to practice the curved arrows as much as possible, because we're going to not just use them to show resonance, as we've been doing, or to show acid-base reactions, as we have here. We're also going to use them to show a variety of other reactions. It's the main way that chemists communicate about which bonds are breaking and how in reactions. And so we really want to get used to that and be able to communicate effectively with them. So here's an example, another example. Here I've got OH minus, classic base. Here I've got a carboxylic acid. What makes this acidic is that the proton is susceptible to being picked off. Right? So the arrows start on a pair of electrons. They point to the atom that those electrons are about to be shared with, and they're shared then in one of those OH bonds. This arrow shows this pair of electrons staying behind as the oxygen, existing as a lone pair. A lot of times we like to try to make things sound exciting. So if two molecules collide and one of those molecules uses a lone pair to form a new bond with something from the other one, we say that one the base attacks the acid, and there'll be other things that we see attacking later in the semester. Attacking just means that it's using a lone pair to pick off something or form a new bond and maybe push something out the other side. This always occurs in one step, and so I always need two arrows simultaneously. Right? I can't pick off the hydrogen unless the other electrons stay behind, because hydrogen can never have two bonds at once. And I can't have these electrons stay behind until the new ones come in. Because if this pair stayed behind and the hydrogen were all by itself with no electrons, it'd be really unstable. So this molecule is not going to give away this hydrogen until the other one comes and attacks it or collides with it, so the new bond can form at the same time the old bond is breaking. And that is a key thing that your mechanism should reflect. And so to reflect that in the mechanism, you need both arrows simultaneously. So let's look at the curved arrows here. We already did this one, but this is a base in water. So as we said, it would pick up a proton, and these electrons would stay behind. That's it. 2 arrows, one to show the new bond and one to show the old bond breaking. So you definitely want to practice that. Here's a more complicated mechanism. This is a mechanism that we'll see later in the semester. It's an elimination reaction where I have this molecule and I'm eliminating the OH and I'm eliminating this hydrogen here. When I eliminate those 2 groups, I form a double bond between the 2 carbons that used to hold those 2 groups. So that's not really what we're trying to focus on right now. We're focusing on the acid-base steps or the proton transfer steps. Right, so what do we have here? We've got some arrows. So what are these 2 arrows showing? Is this an acid-base reaction here? Absolutely. The lone pair is picking up a proton. It's now bonded there. This pair of electrons stays behind. This is a proton transfer or an acid-base reaction. Which one's the acid? Which one's the base? This one is the base because it's picking up a proton. This one's the acid because it's releasing that proton. Once the proton is transferred over to the oxygen, then the next thing that happens in this mechanism, this arrow is showing us. It's showing that this pair of electrons is breaking away from the carbon and moving to the oxygen to become a lone pair on the oxygen. Is that an acid-base reaction? No. It's not a proton transfer, it's simply one bond breaking. One atom pulling a pair of electrons away from another. That's not an acid-base reaction. Acid-base reaction involves a proton transfer. So this one is an acid-base reaction, this one is not. What about the third step here? Yeah, that one's an acid-base reaction because this proton is being picked up by a lone pair and the electrons are staying behind. So this one is acting as an acid. It's losing the proton. It's keeping the electrons that it was sharing with that hydrogen behind. That's what always happens for an acid. This one is acting as a base. Its lone pair is picking up a proton and now has that lone pair shared with the hydrogen that it didn't have shared before. So here's a mechanism for a complete reaction where 2 of the 3 steps involved are acid-base reactions. So it just illustrates how important acid-base reactions are as we talk about other reactions in more detail moving forward. So here was the second quiz question. We're looking at curved arrows. I want to draw the curved arrows in here for the following acid-base reaction. We got to predict which is going to be the acid, which is going to be the base. So one option is I could imagine this lone pair picking up this proton, but if the oxygen shares all 4 of its electrons, it's going to take on a +2 charge, and a formal charge of +2 is going to be pretty unstable. So that's not really a reasonable option. Oops. So instead, what we expect to happen is, so that's another reason why it's really valuable to be able to draw formal charges in there. Because when you can see the formal charge, that helps you to understand what might happen, right? If this is already unstable with a positive, I don't expect it to start sharing more electrons and become even more positive. I expect it to start grabbing its own electrons and holding them back. I expect it to share a smaller number of electrons so it has more all to itself to balance that charge. So that's what prompts me to recognize that this is going to be a good acid. It's likely that this molecule will react as an acid and keep its electrons behind to balance out that charge. And so at the same time, the only site where this molecule could act as a base is at this lone pair. Because what a base does is it uses a lone pair to pick up a proton. So I would use one arrow to show the lone pair starting to form the new bond with the hydrogen. At the same time, the old bond breaks and becomes a lone pair on the oxygen. So to draw those structures then that would result, this oxygen now would have two lone pairs because it already had one, and the other pair of electrons staying behind is a lone pair. And the other product, this pair of electrons would pick up that proton. It already had one hydrogen and a CH2CH3 group and a lone pair. And now when I calculate the formal charge, I'll find this oxygen ends up being positive. So be careful with your formal charges. One way you can check your formal charges, at least to some degree, is to make sure that the total charge on both sides are equal. The total charge should not change. You're not losing or gaining electrons entirely, you're just transferring something over. So we still have all the same particles there, it should still give the same overall charge. So if I have two molecules where one was positive and the other was neutral, I still need some positive, one positive overall only. Just to label them, this would be the conjugate base of the original structure it came from, because it loses a proton and now it could pick that proton back up with one of its lone pairs. And this would be my conjugate acid, right? An acid is a molecule that has the capacity to donate an H+. And so by this oxygen picking up a second H+, it now has the potential to possibly donate it. Right? None of these proton transfers are ever going to be permanent. They all have the potential to be lost or gained any time. So that's what makes this an acid, is its potential to lose that proton and go back to its original form and alleviate that positive charge that it's now carrying. Alright, so the last bit of what we're going to talk about today and leading into next week has to do with how do we judge the strength of an acid or a base. So if you recall from general chemistry, the word strong has a very specific meaning. If something is strong, that means it reacts about 100% in water. That means if I have a strong acid, for example, that acid, virtually every molecule I put in water will donate a proton to water. Almost every single molecule will react. Or as far as the calculations go, I can assume every molecule reacts. If it's weak, then significantly less than 100% of the molecules added to water react. There are varying degrees of weak. Right? So one molecule might react with water, only maybe a tiny fraction of the molecules react. That would be very weak. Another molecule I put in water, half the molecules might react. Well, that would be stronger. Right? So there are different degrees. And if you recall from general chemistry, we said, unfortunately, we can't use the percentage reacting to tell us how strong something is. That would be nice, right? It's very intuitive for me to say, well, I put this acid in water, half the molecules react, so it's a relatively strong acid. If I put this other acid in water and only 1% of the molecules react, it's a very weak acid. The problem with that is when I put a structure in water, I'll just make one up. So let's just say I've got this molecule here. I put this in water. It's a weak acid. Some of the molecules react and some don't. What percentage reacts? Well, it's not always the same. That's the problem. So if this acid is weak, I can't say no matter what, when I put this in water, only 5% of the molecules will react. Because it depends on the concentration. So the percentage that reacts with water depends on the molarity of the acid. That's why in Gen Chem 2 we had to do ice tables. We needed the ice tables to tell us how much was reacting. The percent reacting was not constant. It would change depending on the starting molarity of the acid. But what was constant was the Ka value. So I can use Ka or the negative log, the negative log of Ka which is the same as pKa. Those are the values that describe how strong or weak an acid is that don't change with molarity, or really anything. Well, they do change with the solvent, I should say. But as long as we're just working with water, the pKa or the Ka won't change. It changes actually when you change the temperature, so it does change. But it doesn't change with molarity, like the percent reacting changes with molarity. So if we want to quantitatively judge the strength of an acid, we're going to use the Ka or the pKa. So we're going to talk about that a little bit today. And then next week we're going to talk about how to judge how strong an acid is by looking at the structure. So we're going to look at the structure of the molecule and look at features of the structure of the molecule that will tell us how to rank strengths of acids if we don't have their pKa values. Right? So if we have the pKa values, what we're going to talk about now will allow us to tell which acids are stronger and which are weaker. But if we don't, we'll talk about that next time. So if you recall from Gen Chem again, generically we know an acid's often written as HA. It's something that has a proton that could be donated to water, right? So if we think of HA reacting with water, the reaction would involve the lone pair picking up the proton and these electrons staying behind. Those would be the curved arrows way to show the bond breaking and forming. When I put 100 molecules in water, what percentage reacts? Well, it depends on the molarity, so that's not really a good way to say how strong the acid is. A better way to say how strong the acid is to look at its Ka value. So if you remember equilibrium constants, that was probably a while ago, but the equilibrium constant, any equilibrium constant, is equal to product molarity, right? Recall we use these bracket symbols to indicate moles per liter or molarity. So molarity of all the products multiplied together divided by the molarity of the reactants multiplied together. And also remember, if there was a coefficient here, so if it wasn't a 1, it was a 2 or something, that would become an exponent. So typically in an acid-base reaction, the molecules react in a 1-to-1 ratio, producing products in a 1-to-1 ratio. So usually all the exponents are 1. So that's why we don't have anything squared or anything here. All the exponents are 1. But we take the products and multiply those together on top of the fraction, and we divide by the reactants, and we exclude water because we exclude water, we exclude liquids and solids from the equilibrium constant expression. So we have our solute products multiplied together divided by our solute reactant. And that's the ratio. That ratio should be a constant. And the larger that ratio, the stronger the acid, right? Because if almost every molecule I put in reacts, I'm going to get a lot of products. And the ratio of lots of products divided by a tiny amount of remaining reactant is going to give me a very large number. So the larger the value for Ka, the stronger the acid. At whatever molarity I put in, I should always get the same for Ka. So what are some typical values for Ka? Well, Ka's range over a very large range of numbers. The strongest acids have very large values for Ka. So one of my strongest acids would have a value of Ka of 10 to the 10th. That means there'd be about 10 billion products for every one remaining reactant. Well, that's effectively a 100% reaction, right? If every molecule, for every 10 billion molecules that react, only one doesn't, well, that's essentially all the molecules reacting for all intents and purposes. On the other end of the, so that's like my strongest acid. On the other end of the scale, 10 to the minus 50th, well, that would imply that for every one molecule product that forms, there are still 10 to the 50th reactants. Right? 1 divided by 10 to the 50th gives me 10 to the negative 50th. So my value for Ka is going to be a large negative exponent if the amount of reactant remaining is much, much higher than the amount of product formed. And so this, for all intents and purposes, is a situation where it's not really even an acid. If almost, like 10 to the 50th molecules is a huge number of molecules. It's like way more than a mole. So most of the time, I don't even have that many molecules around. But a ratio of 1 product for every 10 to the 50th reactants is essentially nothing reacting. So these are extremely weak. So we've got molecules that basically don't react at all in water to molecules where almost every single molecule reacts with water. And so when we're dealing with a scale that goes from such tiny, tiny values to such large values, those values are difficult to relate to. And that's why the pKa scale was developed. Right? So it's depending on how mathematical your brain is, these numbers may be relatable, probably not. And how big is 10 to the minus 50? It's so small it's hard to even imagine having a point with 50 zeros and then a number. Like that's like too small to really wrap your brain around, at least for me. So what we'll do with these is we'll take the negative log of these values. So if I take the negative log of 10 to the minus 50th, I get 50. If I take the negative log of 10 to the 10th, I get negative 10. So while the Ka scale ranges from very weak to very strong acids, the very strong acids, when I take their negative log, give me negative values. So the scale gets reversed. The stronger the acid, the larger its Ka value, and the smaller its pKa value. The weaker the acid, the smaller its Ka value. Notice all the Ka values are always positive because it's a ratio of molarities. I can't have a negative molarity and I can never have a negative Ka. But the exponent can be negative if the amount of reactant remaining is way more than the amount of product forming. So when I take the negative log of that, the log of that gives me negative 50 and the negative log gives me 50. So these are very, very weak acids. Essentially not even strong enough to react to any measurable amount in water. And so this is a much more relatable scale. Like in my mind I can think about numbers that range from negative 10 to 50 more easily than I can think about numbers that range from negative 10 to the negative 50th to 10 to the 10th. The problem is I have to remember that this is a log-based scale, which means that one unit on this scale is really a factor of 10 difference in how strong the acid is. Right? So I know that if I have a very strong acid, it's going to have a negative pKa, but if I'm comparing negative 9 versus negative 10, it seems like they're really close. But one unit difference is actually a factor of 10. So the strongest acids always have the lowest pKa values because of the way the math works that we just described. And pretty much the strong acids won't have such low pKa values, they'll actually end up being negative. So let me come back to that quiz question. Let me talk about this for a minute real quick first. So there are a lot of acids with a lot of different pKa values. This is only showing a few of them. There's more in your textbook and there's like tons and tons online. As we just said, each pKa unit represents a factor of 10. So if I ask you how much stronger, or which is stronger, HCl or H2SO4, and by how much, you could just look at their pKa value. So here's HCl, negative 6. Here's H2SO4, its value is negative 9. So which is stronger? The H2SO4 is stronger. Its pKa value is lower or more negative. And how much stronger is it? Well, it's 2 pKa values lower, or 2 pKa units lower than HCl. You get from negative 7 to negative 9, I got to go down 2 units. Does that mean that H2SO4 is twice as strong as an acid compared to HCl? No. The pKa units represent a power of 10. So 2 pKa units, if I subtract these, like negative 7 minus negative 9, I get 2. Each unit represents a factor of 10. So really I can say H2SO4 is 10 to the second or 100 times stronger. And so you have to take any pKa difference and make that a power of 10 because the pKa is a log-based scale if you want to know how much stronger an acid is versus another acid. Alright, so then let's talk about the last quiz question for today. This question says, if I have a base with an especially large Kb, well, first of all, let's talk about Kb. Right, so a base, whatever the base is, as a structural feature, it's got to have a lone pair that it can use to pick up a proton from an acid. And if I'm judging its Kb, that would be specifically the base reacting with water. So the base would pick up a proton from water. This pair of electrons would stay behind on the oxygen. The products I would get in this equilibrium are now the conjugate acid of the base. Once it picks up that proton, starts sharing electrons with it, it's going to become more positive than it was initially because now it has the positive charge of the proton there. When the water loses a proton to the base, it's acting as an acid. It's forced to because the base is basic. The base is grabbing that proton from it. The water has no choice. The water is left with a negative charge in the form of OH minus. So Kb is going to be equal to these product molarities. So the molarity of the conjugate acid of the base times the molarity of OH minus divided by the molarity of the reactants. Water doesn't count as it's a liquid, it's my solvent. And so we're just dividing that by the molarity of the base. If you recall from Gen Chem, the amounts I plug in here are not initial amounts, they have to be the amounts that exist when it reaches equilibrium. So if this is a strong base, when I put it in water, it's going to almost exclusively go to the product side. And when equilibrium is reached, I'm going to have way more products than reactants. And so if I have large quantities of products and I plug large numbers in here, Kb, just like Ka, is going to be larger if the base is stronger. So if the question tells you you have an especially large Kb, that means you have an especially strong base. And so then the question asks, will its conjugate acid have a relatively low or high pKa? Well, we got to logic our way through here. So if the base is strong because it has an especially large value for Kb, what that means, a strong substance reacts a lot. It reacts in the forward direction. The reason it does that is because the reverse reaction doesn't happen as often, or it doesn't happen to the same extent. So something is strong, that means it's unstable. And sometimes students get confused, and I understand that confusion because the word strong means you can take anything on, you're a strong person, you're a stable person, but that's not really what it means in this context. In this context, strong means that it's very reactive. It forces the water to react with it because it's so unstable. And so if it's unstable, that means its conjugate must be relatively stable or weak. If they were both unstable, then it wouldn't almost exclusively react to the right-hand side, right? The reason I get a large Kb is because I end up with way more products when it reaches equilibrium than reactants. And the only reason I end up with way more of them is because there must be something stable about them, and that's why they accumulate in solution. They're not unstable and they don't react back very much. So that means this acid, the conjugate acid, must be relatively stable. And if it's relatively stable, it's a relatively weak acid. And based on what we just said, that means it has a low Ka. And we take the negative log of a very small number, we get a very high or large value for the pKa. Any questions about that one? So if something's strong, its conjugate must be weak. The stronger and more reactive it is, the weaker and less reactive its conjugate is. And if it's not reactive, it has a small value for its own equilibrium constant, which gets reversed when you take the negative log and creates a large or high value for the negative log of its equilibrium constant. As we just said, the stronger the acid, the weaker its conjugate base. Just like we said, the stronger the base, the weaker its conjugate acid. And we just explained that. If something is strong, that means it's unstable, and so its conjugate must be stable. Right? If something is strong because it reacts, the product, which is the conjugate it reacts into, must be very stable and unlikely to react back. So we can look at this quantitatively. So the last thing we're going to show today is how to get an actual value for these equilibria reactions based on the given pKa's. So if you have pKa values given, they won't be given for bases because bases don't have pKa's, they have pKb's for their base. So if I look at the pKa values in any acid-base equilibrium, the acid is going to have a pKa value, and when the base picks up a proton, the base becomes acidic. It now has an extra proton that it could donate back. So this could pick that proton back up. These electrons shared there would stay behind on the oxygen. And so there's always one acid and only one acid on both sides. There's the original acid and there's the conjugate acid. And so you've got two pKa values to compare for each individual acid. And what we were just saying was, the higher the pKa, the weaker the acid. And if it's weak, it's stable. And so the equilibrium should give more of whatever side is more stable. When we were in Gen Chem and we talked about equilibrium, though, we said there are two factors that affect the equilibrium. One is enthalpy, or how stable, or the potential energy of the reactants and products. And so that's what we're talking about here. If it's more stable, it's got low enthalpy or low potential energy, and that's favored. The other factor we talked about in Gen Chem is entropy, which is always there behind everything, being relevant, sometimes more relevant than other times. So if we're looking at entropy in Gen Chem, the main thing we talked about that affects entropy is the number of particles, right? Because if I have a greater number of particles, there's more variety in the ways they can move around and such. So in a typical acid-base reaction, I have 2 moles of reactants, one of these and one of these, and I have 2 moles of products, one of these and one of these. So if I have equal moles on both sides, then typically, if I have equal moles of products and reactants, then the change in entropy is usually relatively close to 0. Right? I can't look at this and say, well, I've got a lot more variety in the way the particles can move around and be positioned in space on one side or the other, because they're basically the same number of particles. So the entropy is not really a big factor here. And so we're just looking at the stability. So the larger the pKa, the more stable the substance is. So I can just compare these two pKa's and I can say, well, the pKa of the acid on this side is higher than the pKa of the acid on this side, and so this side must be more stable, and when it reaches equilibrium, I'm going to end up with more of this stuff on the product side than I have on the reactant side. And that's what these arrows are indicating. So I might just show you 2 equally lengthed arrows and ask you which arrow should really be longer, or which side should be favored in the equilibrium. It's always going to be the side with the higher pKa value if it's an acid-base reaction. And so this longer arrow is indicating when it does reach equilibrium, I'm going to have more products than I have reactants. But how much more? To figure out how much more products than reactants I have, all I have to do is subtract the pKa values. So whichever side has a higher pKa value, that's the side I'm going to have more of, and that means the reverse reaction is going to be small in comparison. If I want to know how much more products I have versus reactants, I subtract the pKa values. So the larger one minus the smaller one gives me the difference. But I have to remember that the pKa scale is a log-based scale, right? P means negative log. So when I get the difference between those two pKa values, that's actually a factor of 10, or a power of 10, I should say. And so once I subtract the pKa values, that tells me that when this reaches equilibrium, for every one set of reactants, there are going to be 10 to the 34th sets of products. And that is such a lopsided equilibrium, we might not even bother concerning ourselves with the reverse reaction. Right? This hydrogen is way more stable on the carbon than on the oxygen. And the reason for that, which we'll get much more into next time, is because the negative charge on the oxygen is not nearly as stable. It's way more stable than the negative charge on a carbon. And we'll see more about that next time. So for now, we just want to make sure we understand that when we're given two pKa values, the equilibrium will always favor the side with the higher pKa, and the degree to which it will favor that side will be 10 to the power that is equal to the difference between those two pKa values. And that will be 1 to 10 to the 34th ratio in this example. So here was the final quiz question. I've got an acid on this side with the pKa value. I've got an acid on this side with the pKa value. The difference isn't that big, but there is a difference. So if I'm looking at the equilibrium that's created, the side with the higher pKa value is the side that's favored in the equilibrium. Once equilibrium is reached, I'm going to have more products than reactants. How much more? Well, we just subtract the pKa units. 8 minus 5 equals 3. I have to remember that the pKa units are a log-based scale. So really what this is a 10 to the third difference. So that means for every one set of these two reactants, when it reaches equilibrium, I'm going to have 10 to the third of the products. Or 1,000 times more products, 10 to the third times more products than reactants. Pretty straightforward once it's explained, hopefully. Any questions about that? Any questions about anything else? So here are the bullet points from today. Day 5 material. A bunch of practice problems you should try related to the skills we talked about today. Next week, we're going to continue with Chapter 3, and we're going to start to look at all the ways that we can judge the strength of an acid based on the structural features of the molecules themselves. And that's going to get pretty detailed, so I would definitely look into that before lecture so the lecture makes as much sense to you as possible. Alright, so I'm going to stick around here on the Discord channel if anyone does have any questions.